Okay, so everyone, welcome to the Tutte Colloquium. So we're very happy to have Marnie Mishna here today. Many people in the department knows Marnie. She is a professor of mathematics in Simon Fraser University, and she works on enumerative and analytic combinatorics. And today she's going to talk about something about lattice work enumeration. So welcome, Marnie, and take it away.
Thank you very much, Jane, and thank you very much for this invitation. It's always a good opportunity, and I only regret that I can't actually go to Waterloo because I enjoy it when I do go. So today I'm going to talk about a generating function story, and I'll just say that it's a little bit of a love story because I really love generating functions, and that started almost, and this is sorry, Kevin, to say this, but almost 30 years ago when I took what was then called CNO 230. And it has always been a major research interest of me, and it started from that class back in Waterloo. So it's nice to come around and talk about it again. I like this story because it's taken me through algebra and geometry that I really didn't know much about and have had the chance to learn about. So I will sort of show you some of the different aspects that this simple enumeration problem can take you through. And it's been my major research interest over the past 15 years. So, oops. Oh, we're going to talk today about walks, and the definition of a walk is that it's a sequence of steps. Here is an example of taking north, east, south, west steps on an integer lattice, and you take a bunch of steps, and this is what a walk could look like. It starts at that red dot. There's lots of different flavors. We could increase the dimension and look at walks in 3 dimensions or 4 dimensions or however many dimensions you can imagine. We can change the underlying lattice from a rectangular lattice to other shapes. We can ask questions about complete enumeration or asymptotic enumeration. Here, for example, we have an example where we're looking at all of the walks in a certain region of length 2, 3, 4, 5, so on. We can look at not just lattices, but maybe different graphs. The general graph problem is difficult, but if we pick a structured world like Calib graphs, then we can actually say a fair amount, and I'll touch on that later today. And then you could ask yourself, well, is this a fun toy object, or does it appear somehow in the rest of science? And indeed, people have used very simple lattice walk models to model polymers and to model Qs. And even though the models that we're looking at look somewhat like toy models, they've actually been very strong for predicting things like phase transitions in different chemical reactions or choices between queuing models, large scale behavior. Okay, so that's what I'm going to talk about today. The combinatorial object is going to be a walk. Okay. And then the question, which mathematicians, we always, I think this is one of the fundamental math questions that we ask is, okay, can we classify these objects somehow? And that's one of the major themes that I'm going to be looking at is classification. And then the question is, okay, can walks be classified in a meaningful way? Why would we do that? Well, we love to classify things from different species, organizing them to chocolates, to any object that you're looking at in mathematics. It's probably part of some sort of classification, was part of it one day or another. So that's what we're going to do here. We're going to look at classification of lattice paths. And we're going to use enumerative information to do it. Like I said, it's actually a love story about generating functions. So that's what we're going to do. We're going to connect the lattice walks to their generating function. And that brings a connection between a combinatorial world and a formal series world or analytic function world. And then once you're dealing with analytic functions, people have been classifying those in math for ages, right? So you have rational functions, which is a polynomial over a polynomial, algebraic functions, they satisfy a polynomial relation, solutions of linear ODEs, solution of nonlinear ODEs. You have a stratification for functions. So once we have our lattice walk models or universe, we could ask ourselves, how do their generating functions fit in to formal series classification. Now, you also want it to not to be artificial and hope that it's actually catching onto some kind of structure, that it's not just because it's rational that that's interesting, but that is telling you something about the combinatorics. And that's what we will see. What I like about this story is that there is a two-way flow of information, that the combinatorial model, especially the lattice walk problem I'm going to tell you about, has actually driven results in analytic functions and functional equations. That people are looking at certain classes of function and getting insight onto what their singularity structure should be, for example, because of the study of lattice walks. So it's not just that we're using the analytic function world, we're actually also returning to it by guiding where to look next for interesting structure. Okay, so my kind of generating function that I'm most interested in are those that are called D-finite. And that's what I've actually been trying to understand since at least my PhD. So what is a D-finite function? Well, it satisfies a linear differential equation with polynomial coefficients. Okay, you can say that, but what does it actually look like? Algebraic functions are always D-finite. If I have an exponential of a polynomial, that will be D-finite, but an exponential of an exponential is not D-finite. Okay, when you take the derivatives, you're not going to find those nice polynomial coefficients in your linear differential equations. There is a major source of them. If you look at multivariable rational functions and you look at a diagonal, so I'm going to define that in a moment. So if that's meaningful to you, and certainly it is to Steve, but if not, don't worry, I'm going to define that in a moment. But this structure is a very common form for a generating function when we deal with walks. And then that means that a lot of families of walks do have D-finite generating functions. And I'm going to sort of explain that combinatorial source. Generally, they are a signal of structure. So holonomic function is another way, it's not quite a synonym, but essentially of D-finite. And the idea is that they don't appear by random, that if you know that your function is D-finite, there's something in that differential equation, or there's something in the recurrence on the coefficients that is indicating structure. So it's good to understand what that structure is, and it's still mostly an open question. And then going beyond that, I would ask myself the question of looking at algebraic generating functions. These are related to grammars and context-free grammars. But sometimes you have objects that have an algebraic generating function and there is no grammar that you can describe. You can prove that by an asymptotics argument. And then also you can look at things that are not D-finite, but they do satisfy some kind of differential equation. That's another nice class. So next goal, meaning outside of this, after this research project is somehow completed, these are two natural areas to sort of go. Okay, so I promised I would define what is a diagonal. Well, first, when we have a function, we have to talk about a series, and we have to pick one series because, as you know, a given function could have multiple series expansions, depending on what annulus of convergence you're sort of looking at. So let's look at basically a geometric series here, and look at the Taylor series expansion of this rational function here. I hope you can see my pointer, actually. And so you get this series expansion, and what the diagonal is I look at those coefficients when all the exponents are the same. So if I look at when I is equal to j is equal to k, and let's call it n, then I'm going to pull out, or I'm going to create a univariate series from that multivariate function that is its diagonal. Okay, so the diagonal depends on which series expansion you're doing. And in this case, you see here, it gives you the nice trinomials. What we're going to see eventually, but only very briefly, Steve is a real expert in it, so if you're interested, he's good to follow up with, is that when you have something of this form, actually, you can say something about the asymptotics. In this case, the procedure that I will eventually describe or loosely allude to would give an answer of some constant, actually computable constant, 27 to the n to the minus 1. And when you see an n to the minus 1, you can use an argument to say that you know this function is not algebraic, it's transcendental. But that's a kind of argument we're going to use in the future. so I want to start to introduce you to that idea now, is that when you have an asymptotic expansion, it's giving you counting information, it's giving you large scale behavior information, but it's also telling you about where you fit in that hierarchy. That if you are transcendental, that is not algebraic, there are some forms of asymptotics that you can see, like, aha, if I see that form, if I see an n to the minus some integer, I know it's not algebraic. I do know, however, that this is definite. So there is a formal theorem by Lipschitz that's proving that, okay, this is my rational function is definite. If I do this procedure on a multivariate series, I'm going to end up with something that is definite. So I wanted to show you these because that's the structure of our generating functions. It also gives us definiteness as a consequence. And that structure can also give us asymptotic information, which can help us decide if it's transcendental or not. So that's what I want to talk to you about today. Okay, so some of my diagonals won't look like diagonals. They'll look like related operators, like the constant term extraction. So if I have some, here I've done it on a polynomial. If I have some series and I'm looking for the constant term, CT, with respect to X and Y, while here there is, I knew I would have trouble. We have the 3 has no X nor Y, so that is the constant term. The Z is not, I'm carry along the Z like it was a coefficient somehow. Okay, and then I can look at the positive extraction, and there I'm interested in the I could be looking at a Laurent series or a Laurent polynomial, and I want only the terms that actually have positive or greater than 0 exponent. Okay, and in that case, I'm evaluating them afterwards. I'm evaluating X and Y is equal to 1. But those 2 operations you can do if you're interested now. You can check with your just a pencil. You can write those as a diagonal. Okay. So if ever I say, oh, I need to do a positive extraction of a rational function, that is a diagonal. So now you know it has to be definite, and you have to know also that there is a path to finding the asymptotics of the coefficients. So that's my first message. Here's a long-standing open question, somehow the reverse. If I have I can quantify by what I mean by combinatorial, but I won't right now. Are all combinatorial definite functions diagonals of rational functions? Okay, so that was asked by Crystal in 1990, and it's a good question. And I feel like it might be yes, but might be a really interesting pathological example to say no. Okay, so diagonal extraction, I take a univariate object, series development, extract a univariate series, which has a nice pattern from the terms that I've extracted. Okay. All right. Let's go into lattice paths. Okay. So in the models that I look at, I'm going to just give them a very combinatorial framework. It's not really quite the same as Brownian motion, though you can get close to a lot of those results if you want to. But what I'm going to do is think of them as the following. I'm going to have a fixed finite set of possible steps, northeast, southwest, something like that. I'm going to have constraints. You have to stay in the upper quadrant. You have to stay in the upper half plane. You have to stay above a line, something like that. Adding a non-uniform weighting or probability on the steps doesn't significantly change the complexity overall in the problem. Sometimes it can make things easier. Okay, so we're going to code a walk with a monomial. This is how we're getting the generating functions. So for example, let's take this, let's kind of call the simple steps, northeast, southwest. And I take 2 steps, and I could end at the point 1, 1. So I would encode that by x, y. And I might also want to keep track of the length. And so I might have x, y, z squared, because it was a length 2. And then the thing is, if I encode my step set, my finite step set with a Laurent polynomial, multiplication of that Laurent polynomial with itself is simulating the number of walks that I can take, unrestricted walks. So I could get a geometric series here, and the coefficient of z to the n on the series expansion of this rational would have an inventory of all the walks and all of their possible endpoints that can take n steps. okay? So the project has been since I started, I guess, in 2003 to look at all the small step walks in the quarter plane and to try to classify their generating functions. Okay, so there's two kind of walks you might look at: walks that start and end at the origin, and walks that start and end at some arbitrary point. So I've given two little objects that are going to sort of denote that. It's also actually interesting to ask if the number of walks is greater than 0, or that's another interesting question from an algebra perspective. Okay, so this is what it looks like. Simple walks. My step set northeast, southwest. I'm going to represent those as unit vectors. I'm going to start at the origin, walk on the lattice, and I only stay in positive coordinates. Okay, that's what I mean to be restricted to the quarter plane. So this has been a very, very fruitful inquiry, because if I want to classify the generating functions, so here I could classify the counting generating function. So this is going to be all the walks of length n. It's a univariate series. Or I could classify the multivariate generating function, which is walks where I've kept track of the endpoint. Okay, so I just want to know what is the nature of the generating function. So this this was a long project, and certainly I did not finish it on my own. I started in 2007 with Mireille Bousquet-Milou. We published a paper that sort of launched the bigger question and did a lot of the classification of algebraic and D-finite. And then since then, there have been techniques used from probability, from differential Galois theory, from a whole bunch of different areas of very unexpected areas of math have come together to sort of classify these. And here you have it. So algebraic, D-finite, differential algebraic means it satisfies another kind of a polynomial differential equation, and D-transcendental is everything else. So trying to understand what is the structure, what is going on in here. Certainly in D-finite, you can see if you have X and Y symmetry, you're going to have something, but I'm going to try to explain to you where those sort of come from. Okay, so this has been really a remarkable effort. We could interpret this if we want to understand what the pattern is. If we actually look at the simple step in various cones, so instead of changing the steps, we change the region. Actually, that has also been considered as a way to look at the problem, and it's been quite fruitful. And really, as long as your region is defined by some theta, possibly even wandering around, and it's not a multiple of pi over 4, you're going to be nasty. And if it is a multiple of pi over 4, you're going to be nice in some way. Okay, so there's some sort of quantification of what that means. That's another way to look at it. Okay, that doesn't capture all the models that I was looking at, but it is a good understanding of where the structure is coming from. Okay. So it's useful, but it doesn't capture all the models. Okay. So now I'm going to talk to you about a source of different models in algebra. So the basic problem is still always going to be the same. I'm going to have some sort of walk model with a finite set of steps. I'm going to be asking myself, how can I classify the generating function of the number of walks, maybe that come back to the origin, or the number of walks that can end anywhere? And I want to know the asymptotic information. I want to know the classification information. So this is useful in algebraic contexts, because many algebraic objects are products of generators. And that's how we view often algebraic objects. So when you ask, if your question is something like, oh, I want to find the number of ways this algebraic object can be expressed as a product of the generators with some sort of constraint on intermediate products, you're really asking a lattice walk question, right? So if you're asking yourself, when is the product of generators equal to 1? Well, you're asking, well, when can you start and end at the same point somehow? And if you're asking about the number of distinct ways to decompose a product into irreducibles, then you're looking at, counting the number of different ways you could get there. So that's why walks appear very naturally in algebraic contexts. Okay, so now I'm going to talk to you about Cayley graphs to give you one source. So remember, if you have a group, you make a graph. The vertices are the group elements. And if you have an edge between two group elements, that means, your Cayley graph is specified with a group and then some set S. So you have an edge between two elements of your group if there was something in that finite set S that multiplied one to take to the other. So it's easiest to see with an example. So here, my group is the cyclic group of order 8. My generator is going to be X, and my S is going to be X and X inverse. So I can, if I multiply, if I multiply X by X, I get X squared. If I multiply X by X inverse, I get 1. And those are its two adjacent neighbors. That's a Calib graph. I can look at the free group, also generated by X, but now I've got no relations, but I still have X on one side and X inverse on the other. So I have the same S here, but I have a different group. Okay. So a simple walk on the rectangular lattice is also a walk on a Calib graph. If I take a commutative group on two generators and I take, oops, those minus ones are superscripts, not minus, not subtractions. So I take X, X inverse, Y, Y inverse. That is going to give me a simple walk in a rectangular lattice. So that's fitting into one of those models that I was looking at, trying to classify. Yeah, here it is. Okay, so in group theory, you might ask yourself, if I have a product of n generators, how can I identify if it is equal to the identity of the group or not? Okay, so for example, if I gave you this, I said, okay, in the cyclic group of order 8, I give you this string of X's here, is that equal to 1 or not? If I were in person, I would pick on somebody in the front row and make them make a guess, but I won't do that here. But I'm asking you the question. So what would you do? You know what you would do. You would find 8 at a time and sort of cross them out, and then that's how you would do it. So this, in a cyclic group, it's not so hard to figure out a mechanism to answer this question. The free group, also, if I'm looking at X and X inverse, what am I going to do? I'm going to pair the X's and the X inverses bit by bit, maybe almost like making a dict path and seeing if I came back to the origin or not. So I could easily come up with a strategy for figuring that out in this group as well. For an arbitrary group, it could be very difficult though. Well, I'm going to actually consider the enumerative version of this problem, and that's sort of to count, right? Count what is any of these, what is this looking at? This is essentially the same as a walk on the Calib graph that starts and ends at 1. So as I'm going along in my product, I'm saying, okay, multiply by X, multiply by X, multiply by X. So in the Calib graph version of this, I'm going around that cycle, and then I see when I'm stopped, am I at 1? So in the enumerative version of this problem, I'm saying, can you walk on a Calib graph, start at 1 and end at 1? Now, how many ways can you do that? So that's counting the number of words of length n with generated over an alphabet or generated by a finite set of generators, and trying to understand if it takes you back to 1 or not. Okay. So this is called the co-growth sequence, but I'm going to talk about it as excursions. So I'm interested in walks on the Calib graph that start and end at 1. Okay. And then it turns out, and this is kind of really interesting, this is why we do this sort of analytic sorting, give us combinatorial information. The analytic complexity of that generating function of those excursions. So is it algebraic? Is it definite? Is it something else? It actually is related to the difficulty of that word problem. How hard is it to figure out a mechanism to decide if a sequence of words is 1 or not? Okay, and that's going to tell you about the group. So if the group is finite, that generating function is rational. If that group has a free group, a free subgroup of finite index, then its generating function is algebraic. So you see there is a connection. I'm trying to convince you that that classification is worthwhile because it's giving us information about the structure of the group, which is the desired object. Okay, so that's what those graphs are going to look like. So then the question would be, what does it mean if this excursion generating function for walks on a Calib graph is definite? So to get to a bunch of different things, I will just say that it's related to the fact that it's important. It's related to the fact of whether or not a group is amenable, which is a condition on the probability of return slowly going to 1. Amenable groups are somehow small, but you have another family of them. So what was I going to say? Oops. What work I did with Jason Bell, I mean, in practice a few years ago, but a paper came out last year, is saying that, okay, if we know that we have a finitely generated amenable group that has a certain growth condition, then that generating function is not T-finite, okay? So that the T-finiteness is capturing something about the, is related somehow to this amenability. Okay, we prove this by an argument on kind of a straight, using a property of the singularities of D-finite functions. We know a lot about what D-finite function singularity look like. So ultimately, it was an argument on the singularities and using this idea about the probability of return. Okay. And then you have some really neat examples to look at that are not D-finite, because now you just look in those amenable groups of superpolynomial growths, you have some interesting functions, you know they're not D-finite, so what are the generating functions? Where do they fit in the rest of it? Okay, so this is an example from the lamplighter group. It's a neat example, and that's a good open line of inquiry. What on earth do those generating functions actually look like? Okay, so you have this very complicated group, you have excursions on it, you know the generating function is not D-finite, it's got weirdness in its asymptotics. So what are the generating functions? What kind of functions are they? I think it's a very good question. Okay, so I'm just trying to sell this as a place to go to for interesting problems about D-finite functions. Okay, so these turned out to be kind of not D-finite, right? The interesting examples we're looking at were not D-finite. What can we go back to a world where they are D-finite? So I'm going to go back to walk models. I'm going to look at another algebraic source, and I'm going to look at a family of source of problems that is giving me things in that diagonal structure, right? That's something that I understand. And so I want to sort of maximize, the knowledge on both sides. Okay, if I know these objects are going to come from that kind of structure, how much can I say about them? So remember root systems, these show up everywhere, and that they're going to ultimately somehow be connected to D-finiteness would not surprise me in the least, because this is somehow one of those kind of like fundamental structures that transcends many subdisciplines of pure math. So I'm looking at a set of vectors that has geometric properties, okay, and it has to do with a condition on, reflecting your set of vectors in these sort of perpendicular planes of the other vectors. So they have a really, 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 really strong symmetry condition, okay, right? So, and they're classified. Whenever I want something to have this property, I know exactly that it has to be something that is already classified. So again, another existence of classification. Here are the ones in rank 2 that satisfy the root system definition. Okay, using these vectors, we can define something called a Weyl chamber, and we can count walks on that lattice, restricted to some, so on the lattice generated by, these vectors that are restricted to a Weyl chamber. The reflections that sort of fix things are a group, and I'm going to use that group. I'm going to be interested in somehow step sets that are also fixed by that group. And that's actually going to capture a fair number of those models, of those small step models that I was trying to classify. Actually, a fair number of the ones that were D-finite actually fit into this framework in one way or another. They might not look exactly the same, like this A2, we didn't have anything with the triangular lattice, but one of the models in there was, a few of the models in there actually were nice models on triangular lattices, but just then scaled to be on a rectangular lattice. So there's a few of those. There's also some models in here. We'll look at G2 in a second that didn't appear there before. So it's telling us where else we should look. And the nice thing is that all the models that appear this way are going to have they're generating functions that are diagonals of rational functions. So they must be definite. So let's try and see how. Okay, so I'm going to pick one of these systems. I'm going to pick, I'll do it, for example, let's look at A2. Let's generate that lattice and let's look at a step set that is fixed by those reflections. Okay, so I'm going to be interested in, let's take a think of a model that has 6 steps. I started this sort of center here, and I'm going to stay in this. I don't know if you can see, there's actually a subtle difference in the blues here, in just this wedge here. Okay, so that's my restriction. I have a finite step set. I have a fixed region, and I'm interested in the walks that stay in that region. Ultimately, I'm interested in knowing the enumeration information, the generating function, the asymptotic information, the classification of the generating function. Okay, so when I have these step sets that are nicely symmetric across all of these reflections, I can make a really nice combinatorial argument. Okay, this is the reflection principle developed in this context is a nice article of Gessel and Zeilberger, though there's work before then on developing this combinatorial argument. Let's say I have all these 6 steps. I look at a walk that starts, let's say, at this point here. Whoops. At this point here, I take my walk, and then at some point I leave. Okay. So what I'm going to do is I'm going to pair that with a walk that started in this region, did the flip of it. So I flipped this across here, did the flip of this, but then once it touched the axis, it ended the same. So they're going to both end at the same point. They're going to start, they're going to start in different regions, right? But it's still going to be a valid walk. This light brown one is still a valid walk because if I reflect any step in here, it's fine. I can reflect it across this line here, and it's also going to be a valid walk. So I'm going to say that these 2 walks are going to be paired. In fact, I'm going to look at walks starting in all the different little wedges. Okay. And I'm going to have this pairing mechanism. So if I start in here, I might pair with something on this side. I might pair with something on this side. So same thing. So if something never leaves, it's just going to pair with itself. Okay. Then the other piece of information is that it's going to make it a sign reversing involution. So I'm going to say, okay, if I start in here, I'm going to have a positive sign. If I start over here, I'm going to have a negative sign. So if I have a buddy, it's going to have the opposite sign. Okay. And if I don't have a buddy, well then, I mean, it doesn't matter. I still have a sign, but I'm not going to be canceled with anything. Okay, so then the idea is if I take the sum over the walks that start in this wedge and to this wedge and this wedge and this wedge and this wedge and this wedge, I'm going to be able to pair any 2 of them if they've crossed a boundary, and they're going to cancel each other out in that final monomial sum. And the things that survive are going to be the things that never left their region. So this is a way to enumerate things that stay in their region, which is kind of a difficult thing to do when you have multiple boundaries, by instead counting unrestricted walks, but in a little clever way. So this is what it looks like. Here is a different example. I take the sum of walks that are going to stay at these 4 points. They each have different signs. 2 walks, every walk is going to have a unique partner that ends at the same monomial unless they've stayed in the same quadrant. So more than expecting you to recreate that combinatorial argument on short notice, I would say it has a combinatorial origin. I have a combinatorial understanding of what this process is. And then once I do that, I can actually write the generating function and make it as an extraction. So for example, if I want the walks that start and end at the origin and stay in the first quadrant, well, in fact, I'm going to look at the walks that start and end at 1, 1 and never leave this sort of light area, because that's just a shift. And that's going to be an extraction of a rational generating function. So again, I'm trying to give you a combinatorial understanding of what the diagonal looks like, because this extraction, I'm going to be able to write as a diagonal. Okay, so I'm not giving you the intermediate computations here, But what I want you to know is that if I have this setup, if I have this algebraic setup, and there's tons of different Weil groups and there's tons of different models. So this is a huge family of possible models. In every case, I can write their generating function for the walks that end at a specific point, for example, the origin, as a diagonal of a rational function. I can write the generating function for the walks that end on an axis or a boundary as a diagonal of a rational function. And I can write the generating function for the walks that end anywhere as a diagonal of a rational function. And if you look, they're very, very similar. I'm just adding these additional products of 1 minus x, 1 minus y. They're very related. The rest of the function is the same. Okay. So once you have these diagonal expressions, the question is, of course, what can you do with them? Before I do that, I'm going to say that outside of the walks that we were looking at, our G2, for example, here's an example of what a step set looks like. It's not just the simple vectors. A simple vector actually has a complicated meaning to break it down as a sequence of mini steps. So when I want to stay in a given region, actually what it's going to mean is that all those little mini steps must also stay in the region. So the interpretation is more complex when you look at these more exceptional ones, but they're very interesting, but they still have the same structure. I can still set up this enumeration as a rational of a diagonal of a rational function. And then it's giving me, I mean, in all of these cases, it's actually giving me information about multiplicities of different representations, but that's a side note. Okay. So the question was, what can I do with those diagonal sections? And so this is going to be a little bit fast. So let's just go back to what we were doing. Let's just see where we ended off and have that in our mind. So we have this combinatorial picture. We have step sets. We have walks that are staying in some closed region. We've written them as diagonals of rational functions. What can we say about the univariate generating functions or their coefficients when they're in this form? Well, let me remind you, or give you a one-slide summary of a one-semester graduate course about analytic combinatorics. So if you're interested in this, of course, the classic tome is Flageolet and Sedgwick. What's beautiful is that a lot of the computation boils down to two sentences, right? The location of the dominant singularity of a function tells you about the exponential growth of its coefficients, of its Taylor series coefficients, okay? And then the nature of that dominant singularity, is it a pole? Is it a branch cut? What is the order of the pole? That's going to tell you about the sub-exponential growth, okay? So that's a pretty simple principle. Let's see what it looks like in action. So imagine I have, so again, here my C is as written as a Taylor series, and I have a coefficients of Z to the N. I want to say something about the asymptotic growth of those coefficients. So this is, of course, there are more complicated forms in this, but imagine for a moment that you know in advance, as we do for walks, that it's going to be some exponential growth. So that's my rho to the minus n. It's going to be some sub-exponential growth, which is this constant here, and the sub-exponential growth, the minus r. Okay. So very often I want to find the constant, kappa, the exponential growth, rho, and the r. So if I have a rational function with poles, this first picture over here, maybe I've got, I think I've got 8 poles here, red, purple, and let's say that the blue pole is a pole of order 2. If I actually look at the modulus of my function, I can see the poles. I can see, because the function is going off to infinity at a pole, right? So it sort of shoots up like a pole, right? And if it's a pole of order 2, it's much thicker. Okay. On the other hand, here I have what it looks like to be a square root singularity. I'm not going to have these things go off to infinity. I'm going to have sort of a rip when I look at the imaginary component of f of z. Okay. So there's the nature of two different common singularities. Okay. So now I have to try to figure out, is there an equivalent mantra for higher dimensional stuff? Okay, we're interested in doing some sort of extraction on multivariable rational functions. And the answer is yes. And you are very lucky. You guys have an in-house specialist in Steve Meltzer. So the first thing we have to do is try to understand what is even a domain of convergence. I mean, this took me ages to even figure out. So imagine, like before, I have a multivariable rational function, and I've got its Taylor series expansion. I'm interested in the points in C squared xy where this actually converges as a sum. Okay, so that's the domain of convergence. And power series are so nice. This is how you fall in love with generating functions, because power series are so nice. Power series are absolutely convergent. So if that's very nice. So what we can do is we can plot the points, the real points, x, y, where it's convergent, and we can actually get our head around that. I can't plot things in C squared. I can't get ahead of that. But R squared, I can plot and I can understand. So for example, in this example here, just looking at what we know from geometric series, we know that x plus y has to be less than equal to 1, right? So we can get a picture, we can get a picture of the domain of convergence. This isn't it, of course, because it's convergence. Domain of convergence is in C squared. So this is just like a meaningful picture of what it would look like in R squared. So I have this, this is in the open sort of, triangle here, the domain of convergence. And then I can take let's back up one sec. Then I want those points where it actually is singular, right? What is it? What is the multivariable equivalent of a dominant singularity? What's the multivariable equivalent of a singularity? Well, it's going to be a variety, right? The points x and y where where 1 minus xy is 0. So that's going to be a set of points. And it's actually going to be represented in the real plane by this purple region. And then these gray regions are where this series could converge if I took other series expansions, like around other points. So the point is, when I have a rational function, I'm going to only look at easy ones. So I'm going to give you a very, very simplified view. That domain of convergence, I'm going to look at it and I'm going to look at some quantity, and I'm not going to explain why. That's a much longer story. What I'm just going to tell you is when I plot that domain of convergence, I'm going to sort of take a hyperplane and I'm going to go up until I touch it in the first place. And that's going to be a way to visualize what the role in the multivariable thing that is playing that role of that dominant singularity, that was playing that role of the location of the singularity. Okay, so roughly I have this picture, and I mean the way I'm going to use this is not going to be very, it's going to be very subtle. It's mostly to tell you that there is a process that we can go through to find these asymptotics, and it has a geometric picture associated. That I'm going to have some sort of curve that is going to represent my domain of convergence. I'm going to come at it with a hyperplane and look for a point of contact. And if you think about the one-dimensional case, we're doing that in a very simplified way, right? Here I had all of these singularities. The dominant one is going to be this blue one. So my hyperplane is somehow zero-dimensional. It's coming across and it's hitting the first one. And that's how we're finding the dominant singularity. So there is a geometric picture in higher dimensions that is going along with this in the most simplified case. Okay. What I'm trying to tell you to connect to my story is that the formulas that we're going to end up use is that sub-exponential growth is going to be a half integer, okay, in what we're going to do. So let's take a look at how this becomes applied. So here's this model again. Okay, here are the step sets. So imagine I've got this step set. I got a 3-model step set. This is that rational function that I'm trying to take the diagonal of. When I look at that domain of convergence, that boundary of convergence for this variety here, I'm going to have a plane, x is equal to 1, y is equal to 1. So I've represented that here with these dark lines. I've got the variety defined by this polynomial here, and that the image of that I'm looking at is this gray thing here. And then when I find that point where it touches, it's actually in here, and that's going to represent a number of different sort of dominant singularities. But the what I'm going to see is that in this case here is the algebraic, here is the asymptotic growth. I have an n to the 3 halves. And then if I look at the excursions, the walks that start and end at the origin, instead of a 3 halves, I get an m to the 4th. So this I know is transcendental, where actually remarkably, this one is not. So I'm trying to show you that there is actually, if I trace through all of this, I do have a geometric picture explaining why one is algebraic and one is not. And then what does that mean for the step set, et cetera, et cetera. So there, for every walk model, I'm going to associate this geometry of its boundary of convergence, and that's going to give me information, actually a ton of information about the nature of the series, the counting of the series. That's what I'm trying to convey. Okay, I understand that from what I've presented, you could not recreate it. You cannot do it. There is a full book, as I said, by Steve, where you can trace through the details. But this is the part, this is the motivation of it, that there is a geometric picture associated, and it's telling you important information about the nature of the series and the asymptotic information. Okay. That's super dense. That last bit is super dense. I'm just trying to give you a taste. So what else is interesting in this problem? One thing that I'm interested in when we're doing this sorting, something that we've come across is that you have a lot of conditions where the result ends up saying either it's trivial or it's very, very complicated. So let's think of an example that you know already. We just have a general analytic function. You know how, like, if it's analytic and bounded, it's constant. So either you're a general analytic function or you're constant, depending on whether or not you're bounded. So that's one of those conditions where it's either ridiculously simple because it's constant, or it's more complicated. And you know, and the little criteria there is this, is it bounded or not? Another one, if you have a series with positive integer coefficients, as we often do in combinatorics, and you know it converges in the unit disk, then the function is either rational or it has a natural boundary. So remember, if you have a natural boundary, you have like, it's dense in singularity. So if you're dense in singularities, you're not definite. So the idea here is that, okay, you have this condition, you converge in the unit disk, either you're rational, which is the simplest kind of generating function, or you're kind of super nasty, you're not even definite. Okay, so that's over 100 years old. So that's old. So there's been a lot of work recently coming up with these kind of criteria. So a function that will either be rational or hypertranscendental. So it doesn't satisfy an algebraic differential equation. That's the next step after definite. And there's a lot of results here to exploit. Typically, the conditions look like you satisfy a difference equation and a differential equation. And then that's when you sort of get into problems. And the thing is, in a lot of these walk models, we can figure out the conditions on the steps that lead to these kinds of situations. So that's how a lot of these walks were proved to not be differential algebraic, is because they somehow also satisfied a difference equation. Or a P-Mahler equation. There's a whole set of these kind of operators. So that's how we have guided some of the functional research, telling them where to look, what are the kind of criterias, what are the functional equations that you can look at to build these kind of criteria. Okay, so today I showed you a bunch of different ways to induce some classifications. We could look to group theory and look at how groups are classified. Groups have there's lots of classifications of groups. Translating that into a lattice walk problem and doing classification models that way. You looked at representation theory, that's the root systems, that they're telling you a whole class of models that have definite generating functions. Or just looking at these as straight vector problems that you can manipulate to say like, okay, if I look at small steps in the quarter plane, there's only a finite number of models. Can I classify them by brute force somehow? Okay. So a lot of functions that are not definite, but do satisfy differential algebraic functions come up, and they rely very heavily on elliptic curves, and they have elliptic functions in ways to express them. And this seems to be really also driving when things match up and when they don't match up. So my projects are to continue looking at these problems from root systems to sort of make some machinery to do somewhat automatic enumeration, to look at those excursions on Calib graphs. That's with my with Jason, but also my new PhD student, Hagai Liu. And then we're trying, one of my active research groups, we're trying to understand what it means to be differentially algebraic from a combinatorial perspective. If D-finite means you have this nice reflection and you have to do some extraction at some point, if we believe that, then what does it mean when you go beyond that? Is there any structure to find? And thank you very much. That's all I've got time. That's all I have prepared.
Well, thank you, Manny, for this very interesting talk. So, any questions for Manny?
Thank you, guys.
So I have a question, Marnie.
Yeah, of course.
So as you mentioned, there's been a really great effort by you and Mireille and many others over the last while to classify sort of, or come up with tests for what it means to be definite. For instance, you can associate this group to a model, and if the group is finite, then you have a definite generating function. If it's infinite, you have a non-definite generating function. If it's finite and a certain sum associated to the group is 0, then you have an algebraic generating function.
Mm-hmm.
So do you have any conjectures or results about being, for the algebraic ones, for being encoded by context-free grammar? So like there's ones that are algebraic, but not encoded by context-free grammars, right?
They can't be. You actually have that paper of Michal Dromota and Banderier, where they look at which asymptotic growths are compatible with being generated by a grammar. So the ones that, like the Creveris and Gessel.
Yeah, so all 4 of the algebraic ones in
yes,
the
I
short
believe
steps
so.
are not context-free.
The ones that have, you have to look at the asymptotics, but the ones that have like the thirds and the
So Gessel has a
ones,
one that has a over 3 in the numerator. So that one is an example they even use in their paper to show that it's not represented by context-free grammar. But
yes,
other ones like Creveris is a over 2, which is allowed to be represented by a context-free grammar.
Is it all of them? I thought that when I looked at that, there was a reason to exclude the Creveris as well.
Okay, so
I don't know if it was the excursions or if
so
it could
be
one of
so
them.
actually so it could be. So my question was if there is a way to tell which ones are context-free grammars and which ones are not, but you're saying that possibly none of them are anyways.
Yeah, I mean, certainly I mean, I know I'm trying to figure out what you might not already know to try to answer to you, because I know you know that.
I don't know. I don't know anything about this question, I think, except for the Gessel one has a 1/3 in the exponent, which can't.
Oh, no, I mean by also looking at the other straightforward modeling being excluded by the pumping lemma and stuff like that, those are always excluded by the pumping lemma, but that doesn't mean that there's not another structure. But I thought there was one of the Creveris ones, either the excursions or back to an axis or something, which doesn't mean that the other ones might not be. I thought that there was one of those that were excluded as well. Okay. But if you've looked at that and you're familiar with that argument and you tell me that no, that one is fine, then I've misremembered.
I only know just from the asymptotics that you can't immediately.
Yeah, that's what I mean. That's for me, that's the main tool. Yeah.
I see.
And I thought it excluded the Creveris as well.
Okay.
So I misremembered.
Thank you, Steve. So
I do recommend Steve's book if anybody is looking.
Thank you. And Marnie has a book as well, for those look up
Yeah.
for even more sources to read this stuff.
Yeah.
So other questions for Marnie?
Might have been too much.
Well, if it's too much for afternoon on Friday, that's just
Yeah,
unmute ourselves. Unmute ourselves and thank Manny for such great talk. And Manny, so we will start with this informal grad house time. And people normally stay a bit longer for informal discussions. So now I'm going to stop recording.